Our last section talks about modeling with exponential and logarithmic functions. With the calculator involved a lot in these problems, calling back to some of the things we've seen earlier in the chapter, but now being able to solve equations using exponentials and logs to cancel things out. Here we have an investment problem. You're investing $2,000 into an account that earns 2.4%, that's annual percentage rate, that's your interest rate, compounded continuously. Continuous compounding, remember, means we're not just getting this once a day or once a month. We're getting this all the time, just in a continuous fashion. The formula for your continuously compounded interest, the amount that you earn, I always call it the PERT formula. P times E raised to the R or T power. P is your principal, the amount you're investing. R is your interest rate. T is your time in years. E is your exponential constant E. So part A of this question says, how much is in the account after 10 years? Well, let's take what we're given and substitute it in. We find the amount in the account by investing $2,000. That's our principal. The exponential constant there. Remember your 2.4%, when you change that to a decimal, move 2 places to the left. So 0.024 times 10 years. Put that in your calculator. We'll end up with the amount that we earn, $2,000, E 0.024 times 10. $2,542, and I got 50 cents if I round it to dollars and cents. 25.42.50. All right. Type of problem we did earlier in the chapter. Now I want to talk in part B, how long will it take for your money to double? If you start with $2,000, how long until you've got $4,000 in your account? Well, we can set up the same problem, but now we don't know the T. We don't know how many years this is going to take. So we know our starting amount, our principal is $2,000. E, we've got 0.024 for our interest rate. We don't know the time. We don't know T. So we do know that we're going to end up with $4,000 after some period of time. Our money's doubling. So this is the equation we have to solve for T. You can use the graph. You can graph both sides separately and find the intersection point. That's a perfectly good way to do this. I'm going to show you how to solve this without the graph, but by getting an answer at the end that might be in terms of a natural log. So if we want to get T by itself, I need to divide by 2,000 first on both sides. So I got 2 equals E to the 0.04 T power. Now, to get rid of that E, I'm going to take the natural log of both sides. I'm going to take the ln of 2. I'm going to take the ln of E to this power. ln of 2, I don't know what that is. I'm going to squeeze this in over here. ln of 2. ln and E on this side cancel out. So this equals 0.024 times T. And then to solve for T, I'm going to divide both sides by 0.024. Divide by 0.024. And I'll get my answer. Which, without a calculator, we'd have to leave our answer like this. With the calculator, I can type in ln of 2. ln of 2 divided by 0.024 gives me 28.881 years. So it takes almost 29 years in that account for your money to double. Right? So, and again, if you would have graphed this and this and found the intersection, if you've done it correctly, you would have found that same length of time in years there. Okay? So that's a mathematical model for continuously compounded interest that we can solve using exponentials and logs. When we talked about exponential decay problems, we did half-life examples. We talked about half-life of iodine, and I told you my story about my friend. Here we got another half-life problem, carbon-14. This is if you know anything about radiocarbon dating, figuring out how old something is based on the amount of carbon-14 that's in it. This is what's going on here. The half-life of carbon-14 is much, 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 much longer than iodine. 5,715 years for half of that radioactive sample to return to ground state, so it wouldn't be radioactive anymore. And we're going to say we have 75 grams of C14 here at the beginning. How much will still be radioactive in 1,000 years? Again, we've done problems like this before. Reminder, we've got our initial value, 75 grams. Then your decay factor is a half, or 0.5, because only 50% of this will remain radioactive. Instead of just raising it to the 1,000th power, we do 1,000 over the half-life, like that. And then we evaluate this in the calculator. See, 1,000 divided by 5,715. After 1,000 years, I've got 66.434 grams are still going to be radioactive in 1,000 years' time. And that's how they tell how old these things are. They compare how much C14 they expect there to be with what there is now, and they can kind of go backwards and figure out the age of the thing. And it's kind of like what we see in Part B here. We want to know, all right, if you start with this 75 grams, how long will it take until only 20 of those grams are still radioactive? So, starting with 75 grams, the half-life of 5,715 years, how many years will it take? What's the value of T that I can use where I just end up with 20 grams that were radioactive at the end? Here's the equation that I'm trying to solve here. If you're going to do this with a graph, understand that it's going to be a really, really large value of T, because after this many years, half of this is still radioactive. So this would be 37.5 grams. So you have to use a really, really large window, which is fine to do, but you'll have to extend your X max a long way. Let me go try to solve this without that. I'm going to divide both sides by 75 to get started. So we got 0.5 to the T over 5,715 power equals 20 over 75. Let's see if I got it. That's a repeating decimal. I guess I'm just going to leave that. Let me reduce that fraction. 4/15 in my calculator. So now 0.5 to that power is equal 4/15. In order to get rid of that 0.5 on both sides, I'm going to have to take the log base 0.5. I'm definitely going to want the calculator involved here. Log base 0.5 of 4/15. That would cancel that out. Would give me over here T over 5715 equals the log base 0.5 of 4 over 15. If you would have left this as 20 over 75, that'd be okay. And then finally, to solve for T, I'm going to have to multiply by that 5715. Log base 0.5 of 4/15. And now if I want a number out of that's reasonable, if I'm going to use my calculator now, I need to use my change of base formula here because I don't have my log base button. So I have to go log of 4/15 divided by log of 0.5. And then multiply that by 5715. Type that all in my calculator. Let's see, log of 4 over 15. And then divide that by log of 0.5. And don't forget to multiply by that 5715 to solve for T. I've got 10,897.880 years at the end there. Hopefully you can see that in the bottom corner there. Almost 11,000 years it'll take for that 75 grams of carbon-14 to decay down to where only 20 grams are radioactive. So that's how we do that. Again, getting rid of an exponential by using logarithms. So there's a couple of word problems that involve exponentials and logs. The final thing I want to do here is talk about a graphic model of this. What if we have a graph of an exponential function? Here I have something I can definitely tell it's an exponential growth just based on the shape of it. And it says this graph fits the exponential model given here. Y equals a times e to the bx power. I've got to find the values of a and b that make that work. So I've got 2 points on my graph, and I have to use those 2 points to figure out what a and b are. So I'm going to take advantage of the fact that I know when x is 0, y is 3. I'm going to plug that into my model here. I know that y is 3 when x is 0. And let's see if I can simplify that some. Well, this has certainly become e to the 0 power, which is just 1. So that tells me that's a times e to the 0 power. That's a times 1. That's just a is 3. So my y-intercept there becomes my a value. That makes sense if you think about a being the initial value of your exponential function. Well, the initial value there is 3, and then we have exponential growth after that. So the a value is 3, and I've got y equals 3 now, e to the bx power. I still have to find the value of b, and I can do that with my other point. I know that when x is 2, so b times 2 up here, I know that when x is 2, y is 19. And now I can solve this and figure out the value of b. With a calculator, I can use the graph. Without a calculator, I can divide both sides by 3. I got to get rid of my e here, so take the ln of both sides. Cancel that out. Over here, I'll go 2b equals ln of 19 thirds. And then whatever that equals, I would divide it by 2. So, or maybe just think of it as taking a half of it out front there. Take a half of both sides. So 1/2 ln of 19 thirds, like that. You can leave your answer like that without a calculator. If you've got a calculator, you can type that in. Or again, you can graph both sides of this. I've got 0.923 for the decimal. So take those 2 coordinates on your graph. It's really helpful if you know what happens when x equals 0, because you can plug that in right away, and that'll immediately tell you your a, your initial value. Once you know that a, plug it in, use the other point, x and y, to solve for the value of b, what we call our growth factor, our decay factor in there. Okay, so that's the beginning of section 3.5, using exponentials and logs to model functions.